mission to promote. Thank you, Aaron. Ocean-based climate solutions. Obviously, floating offshore wind is a interesting opportunity for the West Coast, and a lot of interest in what this energy source could bring for the West Coast in terms of meeting our climate and energy goals. But of course, there are concerns of the potential effects of offshore wind on the environment, the ocean, and its users. So POET is pleased to host today's webinar, allowing Dr. Kaus Raghukumar from Integral Consulting Incorporated to present some information about a recent study that Integral Consulting performed and released late in 2021. So I'm going to quickly turn this over to Kaus and let him provide a presentation on this study. And we are going to finish with leaving plenty of time to have question and answer. So please use the Q&A function at the bottom of your screen. Post your questions whenever. I will collect those and then moderate a Q&A session at the end using the questions that you've posted. So with that, I'm going to hand it over to Dr. Kaus Raghukumar. It's all yours, Kaus.
Thank you, Jason. Thank you all for attending this. Yeah, I think it's my first time speaking to 140 people, registered people at least. Pretty exciting. Presenting some results from our work funded by the California Energy Commission and the Ocean Protection Council that looks at, takes a preliminary look at offshore wind and upwelling on the US West Coast. This is a highly collaborative team effort, and I do want to acknowledge my team. Our team members include myself, Dr. Grace Chang, and Dr. Tim Nelson from Integral Consulting, Dr. Lawrence Chung, Jesse Roberts, and Dr. Chris Chartrand from Sandia National Labs, and Dr. Mike Jaycox and Dr. Jerome Fischer from NOAA and UCSC, respectively. All of us work in various capacities within the marine energy realm. The work we conduct ranges from operational surveys for offshore and marine energy. We work on resource characterization from wind, wave, and tidal energy. And we also evaluate the effects of marine energy on the environment. Finally, through NOAA and UCSC, Mike and Jerome are spearhead some fundamental studies on advancing our knowledge of upwelling ecosystems. All right, there are several compelling motivations to conduct a study such as this. The first being that we have this tremendous wind energy resource on the West Coast that has been identified as a key energy resource to the tune of about 112 gigawatts. This resource can help us achieve our decarbonization goals, help mitigate climate change, and work towards energy independence. I just recently learned that replacing 5 gigawatts of natural gas by 10 gigawatts of offshore wind can reduce up to 5 million metric tons of greenhouse gases. Finally, there are voter mandates in California through the Assembly Bill 525 and the Senate Bill 100 to achieve certain capacities of offshore wind and renewable energy by 2030 and 2045. A key card in this renewable energy deck is floating offshore wind, which would be located in about 800 to 1,000 meter deep water and about 20 miles offshore. Shown on the map, which on the right, which all of you might be looking at, is just some studies by NREL that shows just key areas along our coast that are very attractive to wind energy development. Of course, if you're looking at wind energy development along or really any energy development anywhere, there are concerns about how this might affect the environment. So it does make sense to ask the question if offshore wind turbine arrays have the potential to affect upwelling. these on the west coast of the U.S., these sustained northwesterly winds is responsible for much of the primary productivity that sustains an extremely rich ecosystem. The commercial and recreational fishing, the maritime economy is valued at about $22 billion. It does behoove us to really understand what the effects of offshore wind might be on the ecosystem. A little primer on how upwelling works for those of you who aren't familiar or who last encountered these processes back in high school or something. Is there's really upwelling is a wind-driven phenomena. When you have winds that blow along the coast, there's really two forms of upwelling. The first is the one that most of us know and love, the coastal upwelling. This arises when you have sustained, constant alongshore winds, which drive through the Earth's rotation the offshore movement of surface waters. These surface waters are then replenished by cold, nutrient-rich waters from offshore. This coastal upwelling typically occurs in a very narrow 10 to 20 kilometer band along the coast. It's a highly energetic phenomena. In addition to this coastal upwelling, there is a second form of upwelling, which many of us might not be that familiar with, is what's called curl-driven upwelling. It occurs over a much broader area than coastal upwelling, but it's not as intense as coastal upwelling. Curl-driven upwelling is typically is driven by a horizontal gradient. So if you have changing alongshore wind speeds as you go offshore, this gradient in the wind speeds drives curl-driven upwelling. In this study, we are going to look at the effects of offshore wind farms on both curl-driven and coastal upwelling. One thing we can start to see now is that when you now introduce an offshore wind farm array, it can affect the wind field in two ways. One is it can reduce through the extraction of energy. It can reduce the alongshore winds, which can potentially affect coastal upwelling because that's driven by alongshore winds, constant alongshore winds. And secondly, it can enhance this offshore gradient by having lower wind speeds in the vicinity of this wind farm array and then normal wind speeds on either side of it. So by enhancing the gradient, it can also affect upwelling. And I'll go into a few more nuances of the interplay of these processes in the subsequent slides. Findings to date, it is a Wednesday afternoon, so if you guys do end up falling asleep after this, I hope you'll at least leave with this information on the slide. The key findings are that changes we see are primarily in the vicinity of the call areas and a little offshore of the call areas. There's really no change we see north of the call areas or south of the call areas. There's no change we see in this 0 to 10 kilometer offshore zone, which is the primary zone for coastal upwelling. The most energetic upwelling processes take place in this zone. We do see a small reduction in upwelling in the 10 to 50 kilometer offshore zone. This reduction is mostly offset or more than offset in some cases by an increase further offshore in this curl-driven upwelling. The net effect is we do see an increase in upwelling or nutrient fluxes over this broad region. I do want to reiterate here that in our studies to date, we only model the physical processes. We model the currents. We model the response of the ocean's physical ocean circulations to changes in the wind field. We do not model the ecosystem. We do not model what the phytoplankton response is, what the zooplankton and fisheries, human use, anything other than physical circulation is not modeled in this study. We would like to do it at some point, but we are not doing it right now. A few details on how we run the models and how we configure them. The first, we start with the wind model. So shown here on the left-hand panel is we model wind energy extraction by wind turbines, shown here as these little black bars. So we have constant winds blowing in a certain direction. We model wind energy extraction. So we have these wakes, or essentially regions of lowered wind speeds due to extraction by each turbine. We then drive an ocean model with these modified surface winds, and then we compute upwelling. We express upwelling in terms of operational metrics, which are put out by NOAA. Our colleague on this team, Mike Jaycox, is responsible for developing and releasing these products on a regular basis. Again, in these three steps I show here, the ecosystem model, ecosystem response, or fisheries or human use as examples are specifically not modeled. A few more details on how we go about the study. We kind of run the models side by side. We run a baseline case, so there's no turbines. We kind of configure an ocean model with kind of canonical wind speeds over a broad region along the West Coast. We compute kind of a baseline estimate of upwelling, 3D currents, temperature, salinity, so on. And then we introduce the wind turbine model, where we model extraction of energy by these wind farms. We come up with modified wind speeds, and then we drive the same ocean model with these modified wind speeds, all else being constant, and compute new upwelling metrics, 3D currents, temperature, so on. And then we look at changes relative to the baseline case in upwelling and nutrient supply along the West Coast. A little caveat there is that the nutrient supply that I'll show you and that we compute is inferred from a temperature nitrate relationship which exists at depths. We do not model nutrient uptake by biology. It is purely inferred from this nitrate temperature relationship which exists at depth. All right, shown here are the model domains. We have a kind of a large scale model domain, a coarser resolution model domain, which is kind of this entire picture you see here. And inside of this, we nest a higher resolution model domain within which are present the 2 or 3 call areas we model. So Humboldt, Morro Bay, and Diablo Canyon. We use some pretty high resolution, high quality outer wind fields to kind of drive the models in the outer domain, and then we configure our atmospheric models to produce modified wind fields, which we then drive the models again with. The models that we specifically use are 2 open source community models. Anyone can download them, anyone can configure them, anyone can use them. The atmospheric model is called the WRF model, Weather Research and Forecasting Model. It's routinely used in operational forecasting, meteorological forecasting. It's used extensively in wind farm research and development. It's been used for resource assessment on land and over water, estimates of power production, environmental effects, so on. So it's a well validated, extensively used model that's been in use for 10 plus years now. The ocean model we use is also open source community model. It's called a regional ocean modeling system, ROMS. That's also used all over the world for regional scale ocean circulation, ecosystem models, sediment transport, waves. It's been coupled to Earth system models for climate change predictions. It's got a long, rich history worldwide and along the West Coast. Many of the NOAA's ocean observing systems use ROMS for their model forecasts, and the specific configuration of ROMS used in this model, used in this study, sorry, comes from some operational exercises. Shown here is a turbine build-out. On the left, on the left, we see the vertical extent. They're fairly large turbines, hub height of about 145 meters. We place wind farms in a fairly dense spacing at 3 call areas: Humboldt, Morro Bay, and Diablo Canyon. In addition to looking at this dense build out at these 3 sites, we also look at another build out that includes just Humboldt and a slightly smaller Morro Bay call area. We use an extremely dense spacing of turbines, as dense as we can possibly get. We kind of maintain standard industry spacing between turbines, but the number of turbines in a call area is we kind of squeeze as many turbines as possible. We kind of want to look at this one extreme end member as far as responses of the wind field and ocean circulation goes, but we do recognize that any realistic build out will really start with 1, 2, 5, 10 turbines and go up from there. We don't want to caveat that any results we find in this study do kind of represent just this one extreme end member for a range of possible scenarios and turbine build-outs that one can conduct in these kinds of modeling exercises. All right, I'm going to jump right into some results now. We're going to start with some results from the atmospheric model. We look at wind speed changes. So we run the model over a 25-year period. We look at seasonal winds. So baseline case is this upper row here. The modified case is the lower row here. These cool colors indicate reductions in wind speeds. Warm colors indicate increases in wind speed once turbines are introduced. So a couple of things to point out is that we see little to no change up in the smaller Humboldt call area, which in our case has about 150 turbines. Most of the changes we see are further south, where we have these 2 large call areas adjacent to each other. The changes are mainly in the form of reductions, and in the peak in the season where you have the strongest wind speeds of the spring season, the awake, or the area over which we see reductions in wind speeds, extends just a little past point conception. Changes are fairly modest in a 0.5 to 1 meter range, and again, most prominent in the spring and the summer. Additionally, while most of the changes we see to the wind speeds are in the form of reductions, we also see a small increase in wind speeds in the immediate vicinity of either call area. We attribute this increase to a speed up of wind speeds around turbine blades, which is kind of similar to a speed up around airplane wingtips. This increase, though, is even more modest than the decrease as far as the magnitude of the change goes, with the primary effect being this decrease in the lee of the call areas. Shown here is a zoom. We look at changes in the spring season, that being the season of strongest winds, in 3 call areas now. We have introduced the smaller Morro Bay 376 call area, which is kind of which is the more realistic of the Morro Bay Diablo Canyon turbine build-outs, primarily because of Department of Defense concerns about the use of Diablo Canyon as a wind energy area. So we look at the changes in wind speeds. They're fairly modest around Humboldt, a little more pronounced for this Morro Bay, Diablo call area. And when we remove Diablo Canyon, the changes are even more modest now for just Morro Bay. The wake is a little more well-defined. It's not quite broken up by this region of increase around Diablo Canyon, which we had seen earlier. But now it's just a modest increase and then a smaller decrease. The wake for Morro Bay 376, as we call it, is also substantially smaller than the Diablo Canyon wake. All right, so I mentioned that several slides ago that upwelling is primarily a wind-driven phenomenon. So before we kind of couple our wind fields to an ocean model, we kind of took a preliminary look at vertical velocities induced in the ocean through these wind fields. We were able to separate the vertical velocities from the wind fields into the two different processes I talked about, the coastal upwelling and the curl-driven upwelling. Now, you may recall that the coastal upwelling is the intense upwelling phenomena in a narrow band along the coast, while curl-driven upwelling is not as intense but occurs over a much larger offshore region. We see that in this left-hand column, where I'm showing you vertical velocities in the ocean, positive values denoting upwelling velocities, negative values denoting downwelling. And then same for curl-driven vertical velocities in this lower left. Please note that the vertical velocities for curl are about half as intense as that from the coastal upwelling, but they do occur, as I mentioned, over a much larger area offshore. On the right-hand column is the difference in vertical velocities once turbines are introduced. So purple-like colors denote reduced upwelling, or reduced vertical velocities. Green-like colors denote increases in upwelling or increases in vertical velocities once turbines are introduced. So we can see right away that for just this coastal upwelling, or this narrow, intense upwelling that occurs near shore, we do see some changes. They're primarily down near Point Conception, where the reductions are in this really narrow zone, narrow region, on the order of about 1 meter per day. However, the increases in the changes in curl are much more interesting, in the sense that we have reductions in vertical velocities on one side of the wind farm, which is accompanied by increases in vertical velocities on the other side of the wind farm. So essentially what this is telling us is that there's this interplay between increases and decreases that I will show you in a little more detail in subsequent slides, particularly from the point of view of these operational upwelling metrics. So the metrics we compute are released by NOAA, as I mentioned, on a regular basis. They have a long history, and the two metrics we look at are the coastal upwelling transport index, which tells us the strength of upwelling. So it tells us just how strong, or how much, what the volume of water is being upwelled. The second metric is this biologically effective upwelling transport index, or BEAUTY, which gives us an estimate of the nitrate flux into the upper layers of the ocean. We estimate nitrate flux, as I mentioned earlier, by relating temperature to nitrate, and not explicitly from a model where you have inputs or uptake of nutrients by phytoplankton and so on. All right, so shown here are maps of just the baseline upwelling strength metric, CUTI, and the difference once turbines are introduced on the right. So on the left here, we can see that just baseline case, no turbines. We see some. It's as I mentioned earlier. It's the upwelling is mostly confined, or the most intense upwelling is in this narrow band along the coast. There's certain hot spots, particularly of upwelling, particularly near Cape Mendocino, down in the Big Sur area, by San Francisco Bay. But there is a smaller magnitude upwelling that does occur in this about 100 kilometer zone offshore. Shown on the right is the difference. Positive numbers indicate a reduction in upwelling. The negative numbers indicate an increase in upwelling. So greens indicate a reduction in upwelling. Purples indicate a decrease in upwelling. So so we can see right away that you have this dipole-like pattern. So a reduction on one side of the wind farm, an increase on the other side of the wind farm. These changes are mostly confined, or really are only just confined to this immediate area around the wind farm of Morro Bay, Diablo Canyon. There's little to no change up near Humboldt. And again, we think this primarily has to do with the fact that each call area down here that we model is about twice as big as the Humboldt call area. And the fact that these two large call areas adjacent to each other does tend to magnify effects to upwelling in this region. But it's not clear now to just looking at this map whether what the net effect is. So we look at that here, where we look at the effects in two different ways. In this left-hand column here, we look at upwelling at specific distances offshore. The baseline case shown in black, the case with the Morro Bay, Diablo, and Humboldt in the red, and then just Morro Bay, the slightly modified Morro Bay call area, and Humboldt in the blue. The shaded regions represent interannual variability or natural variability in each upwelling metrics. So mainly the goal here was to show that any changes in these metrics at specific distances offshore rarely ever exceed the natural variability of this gray shaded area. The other thing to note is that there's as I mentioned a few times earlier, is there's very little change in either this transport index or the nutrient flux index in this 10 to 20 kilometer zone offshore. There is a reduction as you go further offshore. Sorry, I just realized I've been talking while looking at pointing out to a different slide. Apologies for that. So yeah, we look at these two metrics for upwelling transport index and the nutrient supply index in two ways. One is we look at specific distances offshore. The shaded areas indicate natural variability. We look at the baseline case black, the three call areas red, two call areas blue. Upper panel shows the upwelling transport index, lower panel shows nutrient flux. We see very little change in between 0 and 20 kilometers offshore for both indices. I'm primarily talking about this left-hand column for now, and then I'll switch to these two plots next. Changes that we do see a modest decrease in this 10 to about 50 kilometer zone. The decrease is mainly in the volume transport, not so much in the nutrient flux. And this change is then accompanied by an increase as you go offshore of 50 kilometers. So upwelling is enhanced as you go further offshore. On the right-hand panel here, now we start to look at the cumulative transport indices. So we kind of sum all these values at specific distances. We do recognize that, you know, these phenomena and these processes are not really point-like processes, like they don't exist at specific points in the ocean, but things do tend to get integrated and aggregated over larger areas. So to kind of capture that kind of process, we look at integrated metrics, where we integrate from increasing distances, going from the coast to further offshore. So so here we see that here again, like in this region, 0 to about 20 kilometers offshore, there's very little change. As you go further offshore, when you reach when you look at changes over say a 50-kilometer zone, is when you see the most pronounced changes. But as you go further offshore now, and you start taking into account of these curl-driven processes, things do tend to get offset. And while in this, as far in terms of this volume transport index, there is a reduction. The moment you start getting further offshore than 50 kilometers, we start to see increases as far as this nutrient flux index goes. It's a really interesting process to us, the way these two can start to get decoupled essentially. And we think this has to do with the presence of cooler waters once wind turbines are introduced, cooler waters at depth once wind turbines are introduced into the mix. And I do want to acknowledge that you know, many of you might have seen seen an earlier report we put out with some preliminary results back in December or January this year, where you might have seen this 10 to 15% reduction in upwelling, which was referenced. We do want to point out that preliminary result was really just looking at this 50-kilometer zone. Since then, so really we're looking at just one data point. Since then, we've kind of taken a deeper look, a deeper dive into our results, and we start to see that like we really need to be considering this large zone and looking at changes over multiple distances, or even a single distance that encapsulates the entire upwelling region, such as this 100-kilometer zone. In that zone, as I mentioned, changes are much more modest as far as the volume transport goes, or even an increase in nutrient supply as far as the nutrient flux index goes. Finally, I'm at the end of my slides. I wanted to leave a good 20+ minutes for questions and answering questions. So to kind of reiterate our findings, no real change in this narrow zone along the coast, which is typically the region of strongest upwelling. A modest reduction in this 10 to 50-kilometer zone, increases further offshore, with the net result is that there's an increase in upwelling over this 100-kilometer zone. All these changes are really in the vicinity of the call areas, and no changes either north or south of the call areas. Our future work as far as this project goes is to kind of add these additional call areas, Mendocino, and continue to look at these metrics for these call areas. What we are currently not scoped to do is to go further and add and start to look at ecosystem responses, ecosystem effects, including that to fisheries and socioeconomics. We'd love to do this at some point, but it's not currently within this study scope. We do recognize that based on what we're finding so far, it would be of a lot of interest to understand what these effects might be and be able to pinpoint any effects specifically, as opposed to trying to infer ecosystem effects from this study of physical circulation, which we don't think is the right thing to do. If you need to reach me, my emails appear. we do have some results which have come out of the study so far. A paper came out a couple of weeks ago on the atmospheric circulation aspect of this study, and our preliminary results from last December are available at the on the Ocean Protection Council website.
House, thank you so much. A couple of things here. We're starting to get a couple more questions. Would folks go ahead and use that Q&A function to post your questions, which we will collect and provide Kals an opportunity to respond to over the next 20-25 minutes. Kals, let me start. Would you help me out, and I expect others on the call, maybe backing up a few slides? Will you please describe a little the one where you're looking at CUTI and Beauty, wonderful acronyms. Could you explain for me and others on the call the significance of these two acronyms, how they relate a little bit better?
Sure. Yeah, so a CUTI is an estimate of volume transfer of volume transport. So when you have cold waters being upwelled close to the surface, it gives you an estimate of the flux of that water, just how much of the water is being upwelled. The second one it tells you what the nutrient content of that water is. So if the water is coming from much deeper depths, it can have a higher nutrient concentration than if the water were being upwelled from higher up in the water column. So a Beauty essentially tells you what the nitrate content of nitrate or nutrient content of those upwelled waters are. So that's the primary difference between CUTI and Beauty.
Great. Okay, that was helpful. So we are starting to collect a few questions, and I'll just go ahead and take these in the order that I received them. So first question: why didn't you study a range? Why did you not study a range of turbine numbers? These densities seem extreme.
Yes, yeah, which is a great question. We kind of followed standard practices in these kinds of studies where we're given populated it as closely as possible with turbines following a standard 7 or 9 diameter spacing between turbines. It's in our kind of next steps to look at slightly reduced density build-outs. But these do represent, we do acknowledge that this is just one possible build-out scenario, the most dense possible one out of a range of scenarios.
Excellent, thank you. Second question: what was the specific reason the dipole effect worked the way it did around the studied wind farms?
Great question. So really, I'm going to go back one slide here, or two. Basically, that dipole of the wind stress curl or curl-driven upwelling is determined, or the sign of the upwelling. So whether it's whether the waters are being upwelled, so deep waters into cold water, deep waters into the surface, or downwelled, so surface waters being driven deeper, either process is determined by the polarity. So whether you go from higher as you go offshore, whether you're going from higher wind speeds to lower or lower to higher. So the sign of that change in wind speeds is what determines upwelling or downwelling. So in our particular case, the sign going offshore through, say, this Diablo Canyon wind farm here, the sign is favorable to upwelling on one side of the wind farm and downwelling on the other side of the wind farm.
Great, thank you. Moving on. How big are the changes in nutrient flux percentage-wise?
So let's look at this. We haven't specifically plotted in terms of changes in percentage, but in this particular plot, say if you look at 100 kilometer at the 100 kilometer swath, we can quite easily compute what these percentages are. Like I'm happy to, these slides will be recorded offline. So before I make some arithmetic errors in a hurry, it's fairly easy to calculate what the percentages are from these curves here.
Thank you. Next question. Have there been reports of algae blooms or increases in algae blooms near wind farms, potentially due to this upwelling?
There's no real operational offshore wind farms out there. Like, there's a pilot one that's being built off of Portugal. There's another one near in the North Sea, but both of those are in very different regions, and they aren't specifically in upwelling like regions. So even if there were reported changes in algae blooms or any other changes there, those changes might not be easily directly translatable to the hypothetical wind farms we are modeling in this study.
Okay, thank you. Next question. You mentioned that variability of the metrics with turbines is within natural variability without them. Have you modeled during both downwelling and upwelling seasons?
Yes. Yeah, so I'm going to jump ahead a few slides, and I'm going to show you a slide. It's nice when someone asks you a question based on the slide that you have as a backup. Let's see. I guess. Oops. Oh, sorry about that. I'm not sure. Okay, there. All right, so shown here, it's a pretty busy plot, which is the reason why it's a backup. Is we look at changes in CUTI and changes in beauty in the face of natural. Actually, I'll back up a little bit. So shown here is our changes in CUTI and beauty in the absence of turbines, blue line, and the presence of turbines in the red line. In both cases, we see each metric can either increase or decrease depending on what the regime in that particular year is. So, for example, El Nino like year around 97, 98. It could be a downwelling year in the absence of turbines, which then transitions to an upwelling year once turbines are introduced. It could be the opposite in a different year, or there could be very little change in certain years. There's a fair amount of natural variability based on natural cycles, like the El Nino Southern Oscillation, for example. And we wanted to look at what any changes in either index would be relative to natural variability. So here now we kind of normalize our metrics where we want to, we kind of this upper green line here is when any changes exceed natural variability. So any points in the curve that go over this upper green bar indicate when changes once the turbines are introduced exceed natural variability. It's a fairly busy plot, but essentially, in a nutshell, at these three key latitudes, changes rarely exceed, like for CUTI or 3.2% for beauty. So it's only, say 1.9% of the times that changes in CUTI exceed natural variability, or 3% of the time and changes in beauty exceed natural variability.
Cal, an additional part of that question was, are turbine effects during downwelling more pronounced?
We have a great question. We haven't specifically looked at specific years dominated by upwelling or downwelling, but yeah, I'm happy to question or updated on the specific results. So far, we've kind of looked at large-scale averages like over 25 years, and not yet zoomed into specific years or specific regimes and changes as they apply. Great question, though. Yeah.
Okay, this next person has three short questions. I'm not sure if that makes them dangerous or not. First question is what the upwelling matrix is. Some more details on that.
The upwelling metric. I'm assuming they mean upwelling metric, CUTI and beauty. If that's what they mean, I'm happy to. I think I just clarified that.
I think so. But they actually use the word. They use the word matrix.
I believe, yeah, it might have been my pronunciation that had them think of matrix as opposed to metric.
Okay. Next question. The mesh resolution in kilometers for WRF and ROMs.
3 kilometers inner domain, 10 kilometers outer domain.
Okay. Is there a wave model between wind and ROMs / ocean current?
Yeah, I think I know where the question is going. No, there is no wave model. The reason I think you're asking that question is there is this well-known feedback between the ocean and the lower atmospheric boundary layer, which this model does not capture. It's a one-way coupled model. The atmosphere drives the ocean, but there's no feedback from the ocean back on the atmosphere.
Okay, well, I'm glad we left plenty of time for questions because they continue to flow in. What would be required to extend this work into the Oregon call areas?
Yeah, it's not currently in our scope. We'd love to do that. You know, we'd love to have a West Coast wide build out and see what the changes are. But yeah, it's not currently in our scope in this project funded by the California Energy Commission and Ocean Protection Council. You know, we know how to do this now, but it still doesn't make it an easy lift to just keep adding call areas. So yeah, right. If you find the opportunity, we'd love to do that.
Next question. Can you speculate what the effect of this shift in upwelling might do to marine life? It seems like this might shift biological activity away from where some of the wind farms are located, where upwelling is decreased.
Yeah, you know, we're really in no position to speculate what the ecosystem impacts are. It really takes the application of a specific ecosystem model, because there's all kinds of feedbacks and interrelated processes, which we think we might know how they work based on the physical circulation only, but things do tend to get complicated quickly the moment you start to include an ecosystem model and look at, and you start to see all these effects that you might not have seen before or expected before. So yeah, we can't really speculate what the ecosystem impacts would be, changes would be based on the physical circulation only.
Right. Next question. Could you explain the temporal scope of the modeling? Over what period of time or seasons did the model incorporate data from?
1988 to 2012, 25 years.
Okay. Are the turbine bases, the parts in the water, included in the model when the adjusted wind speed is applied to the ocean surface, or does the adjusted wind speed just blow on ocean without turbines?
Yeah, it's the latter. We simply model energy extraction by the turbines, and we don't model the presence of the physical structure themselves in the ocean. That again is a great follow-on study, but yeah, we're not currently doing that right now.
Okay. Do you expect the wind turbines to have an effect on precipitation? Is this a possible future area of investigation?
Yes, they do. Yeah, you know, I'd point out I'd point the questioner out to a similar study done on a much smaller scale for atmospheric circulation only by Huang and Hall in 2015, funded by California Energy Commission, where they looked at changes in potential changes in precipitation, humidity, for a much smaller hypothetical wind farm off of Bodega Bay in California.
Okay. Could you talk more about how water depths might or might not be part of this modeling?
We do have, it is a three-dimensional model. We do take into account bathymetry, but the does go from near shore all the way to full ocean depths. So any bathymetric effects on upwelling are being captured in this model.
Thank you. The areas modeled are in locations with a very narrow continental shelf. How might the upwelling integrated over the 0 to 100 kilometer distance differ in areas with a wider shelf like Oregon and Washington?
That's another great question. We don't quite know the answer to that. Upwelling is much less pronounced up in Washington than it is down in Oregon. But yeah, it's something we'd love to investigate further.
Okay. How does the model calculate the wind/wake effects from the wind farms?
The atmospheric model, it models the extraction of energy as a reduction in momentum, in the momentum flux. It also accounts for any changes in turbulence. It accounts for turbine wake interactions, turbine wake interactions. But it is it's what's known as it's got a parameterized wind farm module within the model that takes as inputs turbine hub height, turbine rotor diameter, the capacity of the turbine, so 10 or 12 or 15 megawatt turbines, and then based on these specific inputs, it applies an empirically determined wind for each turbine.
You might have already begun to address this, but this person had a couple questions tied together here. So what are the physical assumptions about the turbines? For example, are they always spinning, or are there periods of shutdown? How might these assumptions influence your results in uncertainty?
Which is a great question. They are essentially always spinning. They're always responsive to the winds. There's no shutdowns built into them. They're all oriented the same direction to the wind. I just recently became aware of a few studies looking at wake steering, where they change the orientation of the turbine blades to reduce wakes. So again, a good follow-on study would be to investigate what events like shutdowns or a time varying wind energy extraction or wake steering might have on ocean circulation. Great question.
Given the complexity of ocean physics, validating these findings will be important to have confidence in the results. How would you go about validating such a model? This would be extremely important if these results are being used for wind farm siting and regulatory purposes.
Yeah, great question. It's something we've thought about it in various capacities. In an ideal world, a Cal Coffee type survey study, so California Fisheries Investigation, where they go out along transects every year, multiple times a year, measure temperature, salinity, depths. They measure, they conduct fisheries assessments, and so on. And it's been going on for, I don't know, like 50 plus years. But a similar program would be kind of the Cadillac option for baseline and continued environmental monitoring.
All right, next question. How will coastal upwelling change over the next few decades due to climate change along the California coastline?
We're currently looking at that right now. It's in our scope to kind of identify periods within our 25-year model that bracket certain climatic metrics. So like the mean, the median, the max, as far as wind speed and wind speed changes go, and to infer what the changes might be to turbine-induced ocean circulation at these happy to keep you guys in the loop, or just keep an eye on our work. It's coming.
Just curious about the uncertainty in the estimates, as models all have some degree of uncertainty. Are you able to evaluate the uncertainty in the differences in the upwelling rate?
Well, yeah, the cool thing with a study like this is, the model by itself. So just the model with turbines or model without turbines would have uncertainties, but by conducting identical studies side by side, with all else being the same, we're able to actually cancel out a lot of those model uncertainties.
Okay. Cal, we have 4 questions left. So if we're quick here, maybe we'll get through all of them. So let's keep going. How do you see this work informing the planning of offshore wind development, including in developing avoidance, minimization, and mitigation measures?
Yeah, which is another great question. It'll be awesome to we had a proposal into to NYSERDA to basically factor a couple models such as this into any mitigation plans for wind energy developers. We unfortunately were not invited to a full proposal, but we do think the idea has some legs, where essentially where you could tweak the placement of wind of turbines, the densities, the time of day of operation, so on, and use that as kind of any planning. If you were to think of a feedback mechanism where we have all these controls to make any planning decisions, one input into those controls would be say any changes in upwelling.
Gotcha. Would you describe this as a statistically meaningful change in modeled upwelling?
So the statistically meaningful part is right here on this slide, where we're express changes in upwelling in the face of natural variability. So I think this part here is definitely is a statistically meaningful portion of the study.
Have you looked at the ROM's ocean fields to describe the temperature and salinity structure for an offshore transect through distance?
Yes, we've looked at, a great question. We have looked at the mean temperature cross section. It's going to be in a paper we're working on right now. Essentially, the change we're seeing is that there's modest warming in the 0 to 50 kilometer zone. And then accompanied by modest cooling 50 kilometer offshore to 100 kilometers. So it does track our changes in upwelling.
All right, last question. Is increased upwelling considered to be environmentally positive for marine life?
We're not in a position to make that statement. Yeah.
Understood. Well, look at that. It is 2 o'clock, top of the hour. We got through all of our questions. First of all, I want to thank the participants today for participating and engaging with a lot of great questions. Clearly, there's a lot of interest in this topic, and I think there'll be more work on this. Dr. Raghukumar, I want to thank you for taking time to present the findings from your report. This has been very helpful, and I want to thank the folks at Integral for helping to make this happen. Once again, the Pacific Ocean Energy Trust, a 501c3 nonprofit with a mission to promote ocean-based climate solutions. And of course, that entails responsibly developed marine renewable energy. So we're honored to be able to host this webinar today. Thank you all for your participation and hope you have a good rest of your day. Bye-bye.
Thank you all. Bye.